Hi, welcome to part 2 of this video playlist about the best methods to convert aliphatic alcohols into alkyl fluorides. This presentation is about the use of dialkylaminosulfur trifluorides as deoxyfluorinating reagents. These are among the most common reagents for this reaction, but also for the deoxyfluorination of other functional groups, for example ketones. These reactions are assumed to proceed by intermediate formation of a difluorosulfimedium fluoride, which reacts with the alcohol. The resulting new intermediate can release fluoride once more, whereby a reactive alkoxysulfimedium fluoride is formed. Like alkoxyiminium chlorides, this salt can decompose into an alkyl fluoride and a fluorosulfinamide, if no competing nucleophiles are present in the reaction mixture. Because fluoride is strongly solvated and therefore a poor nucleophile, it is important to keep the concentration of potential competitors as low as possible. This here is a selection of the most common aminosulfur trifluorides used for deoxyfluorinations. The most common reagents of this type include dust and the morpholine and bis-methoxyethylamine analogues of dust, all of them being high-boiling liquids. Recently, it was found that difluorosulfimedium salts such as X-Tal-Fluor are easier to handle in laboratory preparations and more stable than dust and its analogues. For large-scale preparations, however, liquids are generally safer to handle than solids. The main advantages of dialkylaminosulfur trifluorides are the mild reaction conditions, the broad scope, and the high yields achievable. One problematic aspect of dust is its tendency to explode when heated too strongly, but the other common aminosulfur trifluorides seem to be more stable. Then, most of these reagents are quite expensive and generate stoichiometric amounts of fluorine-containing waste. Moreover, these reagents are not very selective, what can be a problem if a given starting alcohol contains more than one hydroxyl group or other functional groups that may be deoxyfluorinated. In this example, a secondary alcohol was converted into the fluoride with retention of configuration by treatment with dust in refluxing benzene. Retention of configuration came probably about by intermediate formation of an oxonium fluoride with one of the ether oxygen atoms. Although the starting alcohol was an acetal and no base was added, no acetal cleavage occurred and the secondary alkyl fluoride was obtained in high yield. Despite the difficulty of displacing the hydroxyl group of cyanohydrines, this reaction can be accomplished by treatment with dust. The cyanohydrine of acetone underwent mostly deoxyfluorination with dust and, in the absence of any solvent, at room temperature. Only 10% of an olefin resulted as elimination byproduct. This example shows that an excess of dust can act as a strong acid. Alpha-hydroxycarboxylic acids tend to decarbonylate when dissolved in sulfuric acid via acyl cation formation. Similarly, the alpha-hydroxy acid of this example underwent decarbonylation when treated with an excess of dust. This decarbonylation could, however, be avoided by starting with the alpha-hydroxy methyl ester instead of the free carboxylic acid. The choice deoxofluor versus dust had probably no effect on the product distribution. In the example on this slide, a carbohydrate-derived acetal-containing secondary alcohol was converted into a fluoride, this time with inversion of configuration. Only a slight excess of deoxofluor was enough to bring about a complete conversion of the starting alcohol. Only a small amount of enol ether was formed as byproduct by beta elimination. This is an interesting example because beta-hydroxy esters readily eliminate water to yield acrylates. Nevertheless, a high yield of fluorosuccinate was obtained with clean inversion of configuration upon treatment of an allylated malic acid diester with dust. So, what can go wrong? If no further bases are added to the reaction mixture, typical side reactions caused by dialkylaminosulfur trifluorides will also include the rearrangement of carbocations. And as already shown in some of the examples, elimination is also a typical side reaction of most deoxyfluorinations, because fluoride is a poor nucleophile but a good base. In this example, in addition to the expected deoxyfluorination, both elimination and migration of the phenyl group took place. As with other deoxyhalogenations, amino alcohols may rearrange by intermediate formation of an aziridinium cation. This also occurred in the example on this slide. Interestingly, fluoride did not attack the benzylic positions or the sterically more accessible methylene group of the aziridinium cation, but the carboxyl group bound carbon atom. One further potential side reaction is allylic rearrangement. In this example, an allylic alcohol containing an acetyl group underwent, upon treatment with dust, allylic rearrangement to yield mainly two products, where fluoride added to the allylic cation from the sterically more accessible side of the ring. The yield of the product formed without allylic rearrangement and with inversion of configuration was only 8%. Further potential side reactions include the deoxyfluorination of carboxylic acids to acyl fluorides and of ketones to geminal difluorides. Dust can also be used to convert acyl or sulfonyl chlorides into the corresponding fluorides. Treatment of sulfoxides with dust brings about a Pummerer-type reaction to yield alpha-fluorinated thioethers. Finally, because fluoride is not very nucleophilic, other nucleophiles present in the reaction mixture or in the starting alcohol can compete with fluoride and yield other substitution products than the expected alkyl fluoride. Here are some more examples of the use of aminosulfur trifluorides for deoxyfluorinations to help you get a feel for the scope of this reaction. The next video is about the use of fluoroalkylamines as deoxyfluorination reagents. These are less reactive but more selective than aminosulfur trifluorides and are often superior if the starting alcohol is structurally complex. So long.